applications of integration to motion, and we're going to look at a non-vector approach. So this is for subjects that aren't doing vectors. It will, however, use calculus. Now, from earlier work, which you've hopefully done, and indeed this is a little snipping from one of my previous videos, we can use differentiation or finding the derivative to, if we have a displacement function in terms of time, we can find the derivative and we can get velocity. And if we have a velocity function in respect to time, we can find the derivative and we can get the acceleration. Of course, if we're given the acceleration, we can find the antiderivative, integrate and get velocity. We can integrate velocity as a function of time, take the antiderivative and integrate to get position. And position and displacement are very closely related, and in this video we'll see examples of both being used. The velocity of a vehicle increases from rest to 80 km per hour in 30 seconds under constant acceleration. So we then have to find the displacement in meters of the vehicle during this time. So the displacement is to do with its change in position, and it suggests in a particular direction. Because the answer is in meters, required answer is in meters, I'm going to convert 80 kilometers per hour to meters per second first. So that's 22.2 recurring meters per second, or 22 2/9 meters per second. The acceleration is a constant, so it's quite simple to come up with that constant. We need to start with the acceleration. So we've got a figure there, 22/27, or about 0.8148 meters per second squared for that constant acceleration. Now, velocity is the integral of acceleration with regards to time. Here we have a constant being integrated. So that's a 27, which equals 22/27 plus constant. Whoops, 22/27 t plus constant. But because it starts from rest, that means at time 0 velocity equals 0. So from the equation up here, the velocity equals being 0 equals 22 times 0 over 27, because t is 0, subbing that into the equation, plus c. Well, c must also be 0. So the velocity function is just 22t over 27, no constant to actually add on there, 22t over 27. So the displacement in this time frame from 0 to 30 seconds in this interval, the displacement is the change in position, and we look at where it started and where it's ended up. By integrating the velocity, a definite integral between 0 and 30, 22 over 27t with regards to time, going through our definite integration, and we get 333 1/3 meters. So it's changed its position by that much, so its displacement is about 333 meters. Second example, out of 3, we've got an object being propelled vertically upwards, that's straight up, and its is already at the 2 meter mark above the reference point, which is the ground, okay? And it's propelled, thrown, projected straight up, starts at the 2 meter mark, and its velocity when it takes off there is 25 meters per second. So that's pretty quick. And whoops, that's meters per second. So we've got to do three things: find the velocity after 2 seconds, then we've got to find when the object first comes to rest, and the position of the object after 3 seconds. So it's scaffolded out for us, it looks, so they tend to be reasonably okay questions to do. Now in questions like this, that 25 meters per second is not a constant, it's just an initial value, and the velocity, when you project something vertically upwards, the velocity will reduce, and we're ignoring air resistance, but we are considering the effect of gravity. Okay, so these sort of questions will make these observations and these assumptions. So that 25 will get less and less, but what makes it become less? The acceleration due to gravity. Okay, now that's going to be considered a negative. Okay, so G is 9.8 meters per second squared. Well, that's the approximated version. Sometimes you'll see questions that just have G in them too, because that makes sense, because G's a little bit different depending on where you go, whether you're at sea level or high in the mountains and so on. The gravitational field varies just a little bit. So, but we're gonna suggest that 9.8 is reasonable. So when we put it in and we want to look at the change in velocity, okay, or in other words, velocity as a function of time, as time changes, we need to look at this thing called G, and its acceleration. So we want to integrate acceleration between 0 and 2, because that's after 2 seconds, from rest until after 2 seconds. So we're looking at that now. That acceleration is considered to be a constant, even though it's the function is a of t there. So what we have, that equals negative 9.8 if we're considering the positive direction is up, negative 9.8 dt. Alright, and so we do our integration, a definite integration, and we'll get negative 19.6. So just before I said the change in velocity implies the velocity as a function of time, we need to do a step here. So in this particular case, for part A, after 2 seconds, we will have the initial velocity. The velocity is the initial velocity, which is 25, plus negative 19.6 meters per second. Okay, that's 5.4 meters per second. So in this case we need to think, what is that v of t function? It will be, in this case, if we always have that same projection speed and up is positive, we'll have 25 plus the integral from 0 to whatever t is of negative 9.8 dt. Okay, so that's always going to be the case for us in this. So that would be 25. If you did the definite integral, okay, when you sub in the lower values, they come to 0, and the upper values would become t, so u plus negative 9.8 t. Okay, and that can be written as 25 take 9.8 t. So just recapping, that's our answer to part A there, and now part B, we're beginning that. Remember, in part B we had to find when the object first comes to rest, so that's when velocity is equal to 0. So we can use our function. When does it come to rest? Well, let's see if we set the velocity equal to 0. So if 0 is 25 take 9.8 t, it's pretty easy. T would, if we did some rearranging and solving, t would be 2.55 seconds. Okay, so it comes to rest after 2.55 seconds. So now for the last part, we've got find the position of the object after 3 seconds. So the position. Okay, so the position, we've got to find the displacement first, so it's how much it's changed its position, and we do that by integrating again. Okay, so displacement, which is often an x, it's the integral of the velocity function that we have there, so 25 take 9.8 t dt. So we need to find its displacement in the first 3 seconds to find its position ultimately, right? So that will be integrating between 0 and 3. Alright, and then we get an antiderivative in here of 25t minus 4.9 t squared. Did you spot where I missed my t there? How's that? Alright. Oops. A bit better. And we've got that in our limits between 0 and 3. And we can evaluate that as 30.9 meters. Okay, so it's changed its position by 30.9 meters. Now remember, it was launched at 2 meters above the ground, so its position, if the reference point is on the ground, its position above ground is what we mean, equals 2 plus 30.9, which is 32.9 meters. Third and final, particles oscillating in a straight line. Its velocity in v meters per second at time t is given by this function here. Now oscillating means it's going backwards and forwards or up and down in a straight line, and that may be what's called simple harmonic motion. So it goes back and forth, or up and down, up and down. Okay, straight line motion. Okay, so we've got v of t given to us. It's a trig function. And get that down there, and we've got to find the particle's displacement between t equals 1 and t equals 4 seconds. Alright, so let's integrate velocity if we want to get a function for displacement. Now, one way we can do this is to deal with the arbitrary constant in an interesting way. But first, we can put this constant out the front of the integral. And rewrite this ever so slightly differently. Okay, now integrating sine ax form is the reciprocal of the a, the constant, the coefficient there, the pi on 2, so it'll be 2 over pi. Now the integral of cos is the integral of sine is negative cos, so that's all going to be negative of pi on 2t. Okay, plus c. Okay, simplifying on the next line, so we've got the 2's cancel, the pi's cancel, we've got negative 3 cos pi on 2t plus c. One way of dealing with this is to find x at t equals 4 and x at 1. So we sub those in. Like so. The assumed constant is the same with both of them, you see, so we want to look at the displacement between there, so we're looking at the difference. Okay, so let's simplify these terms first, but let's partition that off, and we have that'll be negative 3 cos, and that'll, in the brackets, that'll simplify to 2 pi, and then we have negative 3 cos pi on 2. So we have the displacement is the change in those two, so the final minus the first, and we have negative 3. Now cos of pi on 2, alright, is the same as cos of 0, which is 1. So we have negative 3 plus c, now x of 1. So cos of pi on 2 is 0, so we just have 0 plus c. Oh, sorry, it should be a c. That comes out as negative 3 meters. Okay, so that means that the displacement has gone in the, it's moved in the negative direction. So you have to determine one of these directions as positive. That depends on the problem. It's gone in the opposite direction to whatever the positive direction is. So negative 3 meters is its displacement.